So it's already 1 o'clock and participants are still joining. So let's wait for a few minutes so that everyone can join and then we can start, okay? So while we are waiting, I would like to pass some instructions. Everyone, please make sure that you have joined with your names following the naming conventions. It should be your actual first name followed by your last name. So please make sure that you have not joined in with any nickname or your device's name or any enrollment number or something. The another thing is that we will be passing a feedback form. So please make sure that you fill in all the details to tell us how you felt about the workshop or if you want us to improve any further. And it will be followed by your details so that we can make your certificates ready according to them. And we will be following the criteria for the certificates of 60% of attendance of time, which means that you will be considered eligible for the certificates if you have attended the workshop for 60% of its time. Okay, so let's learn and grow together. We still have like 4 minutes. We'll start soon, okay? All right, so looks like everyone's ready. So let's get started. Good afternoon, everyone. On the behalf of KSV and LDRP Institute, I warmly welcome everyone that has joined us in the workshop this afternoon. Before moving forward, let's have a quick introduction about KSV and LDRP Institute. So KSV, Kari Sabha Vishwavidyalaya, is a university established with the Gujarat Act 21 of 2007 and was approved by UGC. The university has been set up by Sarva Vishwavidyalaya Keramani Mandal, a trust with more than 100 years of philanthropic existence to provide need-based education and develop courses of contemporary relevance, to be the university of excellence by providing research and skill-based activities and training which would foster higher economic growth, and to provide education to all irrespective of caste, creed, religion, etc. Now, talking about LDRP Institute of Technology and Research, it was set up in 2005 and 6. The college has made a steady progress from the past 16 years of its existence. As a prestigious state institute, LDRP has long recognized its role in engineering education, generation, and dissemination of useful and relevant technological, industrial, and economical development of the country. And now, KSV and LDRP has brought to you this Break the Barrier event, which is a compilation of various workshops from industry experts, working professionals, experienced developers, CEOs, and more, where you can present your revolutionary ideas and skill up through the competitive environment presented by the hackathon to grab the opportunity to win excited prizes. So among these 14 plus featured workshops, today we'll be having our blockchain workshop. And on that note, I would like to introduce our presenter for the workshop, Mr. Tanay Gupta, a software development intern at Amazon. So without any further ado, I would like to hand over to Mr. Tanay. Good afternoon, Tanay, sir. Grateful to have you on board.
Thank you, Kushbu. Great to be here. I want to thank DTB for having me. So let's start. Share my screen. Is the screen visible?
Yes, it's visible.
Okay. Just a little introduction. Good afternoon. I'm Tanay Gupta. I graduated from BITS Pilani, Hyderabad campus this year with a bachelor's in electronics and communication and a minor's in data science. I'm working at Amazon as a software developer engineer. I want to thank Break the Barrier for having me here. And today we'll be learning about blockchain, why it was created, how it works, and how can we use it. Please feel free to stop me at any point of time to ask any questions you have. And you can even ask me about the business logic behind certain things like smart contracts and how they work. Okay, so let's get started. As for the agenda today, we'll be going over a multitude of topics that include distributed ledgers, blockchain, types of blockchain, consensus mechanisms, Merkle trees, and so on. So we have a lot to cover. So let's get started. Before diving into blockchain, we need to understand distributed ledgers. Blockchains are a subset of distributed ledgers, and they are kind of built on top of them. So when we hear ledgers, we think about records. So ledgers are records, and usually we deal with centralized ledgers. That is, there is a single entity like a bank that has all the records in their servers, and you as a client have access to those servers. Think about a bank that stores all the transactions that you have made and all the withdrawals and credits that you get in the account. Distributed ledgers flip the idea on their head and giving each client ownership of the ledger. That is, the clients are responsible for maintaining their own copy of the system. So as you can see over here, clients themselves have their own copy of ledgers and they themselves maintain it. So an obvious question might arise that, okay, how do we resolve an issue that arises? For example, if say that I pay J 3,000 rupees, but Jay has no record of it in his ledger, how do we know who is telling the truth? The good thing is that in distributed ledgers, participants don't have to trust each other. That is because of the inbuilt mechanism that we have. So through this diagram, I'll explain. When a transaction occurs, let's say me sending Jay 3,000 rupees, I broadcast this transaction to the entire network and essentially announcing to the world that this transaction has occurred. Now, if I try to change the amount I sent to J, like from 3,000 to let's say 6,000 rupees, the change will only be present in my own ledger and not other people's ledger. So there are multiple people. Let's say there's me, Jay, Khushbu, Rohan, and everyone else who's the participant. When I announce that I sent Jay 3,000 rupees, everyone will make a note of it. And now, even if I change the amount from 3,000 rupees to 6,000 rupees, the change will only be there in my own copy and not the copy of other people. So if an issue arises, or let's say there's some malicious node. By node, I mean a client. If there's a malicious node, then people can't be, defrauded in the case. But let's say we only have 3 participants. That is me, Jay, and Khushbu. And let's say Khushbu's ledger should contain the truth. That is, as she's a third party and not considered aligned with either one of us, she should have the truth. But what happens if I, bribe her and say that, okay, I'll give you 1,000 rupees, just change the entry from 3,000 to 6,000, and that way we'll both be happy. Well, surely that can happen. But usually these systems contain thousands of participants. So this process is very difficult, as I cannot bribe everyone to change the entry, right? So an example of this, if you can see that it's an app called Splitwise. So Splitwise, I'm not saying that it exactly uses the distributed database, but I'm saying that it may use it. So for example, what Splitwise does is that it's basically a ledger that keeps track of expenses between friends. So let's say I go to a restaurant with 5 of my friends, I pay 2,000 rupees bill. So everyone owes 400 and so on. So essentially Splitwise does that. So Splitwise can easily use distributed ledgers where everyone can have their own copy, and we'll have the same system that I explained just now. So coming to blockchains from distributed ledgers, here are some similarities and differences. Blockchains
I watched one video. No, not this.
Sorry, is there a question?
So you can continue.
Yeah. Okay. So blockchains are immutable, like whereas distributed ledgers can be mutable. We can change the entries there, but in blockchains we cannot change the entries. Similarly, blockchains have to be decentralized, whereas distributed ledgers can be centralized. It's important to note that decentralized and distributed are not the same thing. Centralized or decentralized deal with the ownership of data, whereas distributed means that the data is present whether at a single location or together. So blockchain has it in a decentralized form. There is no single owner of the data. Many people, like all the participants own their own data. So that's one of the good things. The next thing is transparency. Blockchain will definitely have transparency of data. That is, that when you announce that I paid, let's say, 3,000 rupees to Jay, there is a transparency to the entire process. You cannot, have some anonymity about through it. Like you can have it in a pseudo-anonymous form, like you may be assigned a single ID or something like that, but you cannot hide the transaction. That is, there's transparency. Also, blockchain has security, whereas distributed ledgers may not have security. And when we talk about security, we are not talking about, okay, I have a login page or something like that. By security, I mean whether the paradigm of blockchain has inbuilt security or not. That is, if we have it in its bare bones, that we have a blockchain, we have distributed ledgers in their basic form, do they have security? So in the case of blockchain, yes, distributed ledgers may or may not have security based on their implementation. finally, and the most important thing is blockchain has to use consensus mechanisms. We'll go to consensus mechanisms in a few, after a few slides, we'll go over them. Whereas distributed ledgers may not have consensus mechanisms. Okay, yeah. So here, over this diagram, it beautifully explains the relationship between distributed ledgers, blockchain, and distributed databases. So you can see that distributed databases is kind of the top layer of the onion. When we go to distributed ledgers, we relax the assumption that all the nodes are honest. That is, malicious nodes may be present. So over here, in the example that I gave, where I was paying J 3,000 rupees, but I was showing it as 6,000 rupees later on. So over here, I'll be the malicious node, and the presence of such nodes is assumed. When we go to blockchains, we have complete, we have the complete transaction history. If we take the example of cryptocurrency, that is, each block is cryptographically linked to other blocks. So you cannot change the data in any way. So, and so on. Then when we come to permissioned blockchain, we'll read about those in a few moments. But overall, in permission blockchains, we have permissions as to who can post and who can commit data to the blockchain. Till now, does anyone have any questions? Okay, let's go to blockchains. Okay, blockchains are tamper-evident and tamper-resistant digital ledgers implemented in a distributed fashion. That is, they don't have a central repository, just like distributed ledgers. And they don't have a central authority as well. Blockchains enable community of users to record transactions in a shared ledger within that community, such that under normal operation of the blockchain network, no transaction can be changed once published. Each block is linked to its previous one, so that if you change a single block, then you'll have to change the next ones. So making the entire system tamper evident. As new blocks are added, it becomes harder and harder to modify old blocks. Let me show you how. Over here. Let's say that block 1 contains the transactions that I want. So when you think of a block, blocks are essentially multiple transactions stuffed into a single entity. That's called a block. So let's say we have 1,000 transactions. So a single block will contain those 1,000 interactions. Now let's say I want to change one of those 1,000 interactions and it resides in block 1. If I change that transaction, the hash of the block will change. So what do I mean by hash? Hash is basically a simple formula that produces a result. So hash is usually a string of characters that is generated by a formula, and it's of the same length regardless of the amount of data that you pass. So over here, you can see that we have Fox. It's a cryptographic hash, and we pass it into a cryptographic hash function. You can think of it as a black box, and it outputs a digest. By digest, I simply mean an output. So the hash of Fox is this, DC, DF, CD, and so on. Now, if we have hash like this, the red fox jumps over the blue dog. The hash is this. And what happens if we change just a single letter over here? That is, we changed V to U. You can see the hash completely changes. So you can see that it's sort of random. That is, you can't guess which input will lead to what output. You have to manually enter it and get to know the input. So this is hash. So when I talk about hash of a block, what I mean to say is we have the entire data, that is the previous hash, the data of the block, and so on, and we hash it. And let's say the hash comes out to be this 6U9P2. This is an extremely small hash. Usually hashes are much bigger, but for our sake, let's say this is our hash. Now, when we have another block in the system, we include the previous hash into this block's data. And including that, let's say the hash comes out to be this 8y5c9. And similarly, the third block. Now, let's say that I want to change a single transaction out of the 1,000 transactions that are present in the block. So the hash will change completely. Maybe it becomes over here. Yeah, over here, let's say the hash becomes 7xyvz. Okay, let's say the hash becomes this. Now, this hash will also change, and we'll have the new hash in this space. This will result in this hash changing, and that will change this hash, and so on. So you can see, as we add new blocks, changing of the older data becomes harder and harder. And even if you change your own block, let's say you successfully manage to have 3 hashes, you changed all of these, you updated the data. But think about it, you only changed your own local copy. So over here, we had multiple users, right? We had multiple users. So you managed to change your own copy. So this copy is compromised, but other copies are still relevant and they still contain the true data. So how many copies will you be able to change like this? Now the attacks are still possible, and we'll understand them later on. Do we have any questions till now? Okay. I did not go deep into hashing and cryptography, but as a blockchain developer, it's essential that you guys learn and understand how hashing works and like how in general cryptography in the context of blockchain works. Let's see. In this slide, I'll talk about types of blockchain. So blockchains can be categorized in 2 major ways that are permission based and ownership based. When I talk about permissions, I mean the read, write, and commit permissions. That is, who can read data, who can write data into the blockchain, and who can change the code of the blockchain, who can commit changes, who can change the protocols and stuff like that. And when I talk about public and private, I mean the ownership of the infrastructure, who owns that blockchain. So let's take the first category, that is the public and the permissionless. So you can think about Bitcoin, for example. That is a public platform. That is, no one owns the database, no one owns it, and it's permissionless. That is, anyone can read or write data into Bitcoin network. Bitcoin and blockchain are not the same thing, just to be clear. Bitcoin is based on blockchain and it uses blockchain, and its blockchain is fundamental to its working. So you can think of Bitcoin. So anyone can join Bitcoin, anyone can read the data that's present on the network. Anyone can write data, that is, anyone can make transactions, and once I've made transactions, anyone can write those transactions into the block, provided that you have the capacity to mine the block. And we'll understand that in a bit. And it's hosted on public servers. The entire process is anonymous. Well, it's actually pseudo-anonymous. What I mean by pseudo-anonymous is, as I said, that you have a unique ID. And let's say my ID is 1, Jay's ID is 2. Then when I send the money or anything to Jay, it will show that 1 cent coins to 2. So if you don't know who 1 and 2 represent, in that case, your anonymity is maintained. But there still be some record, like anyone can see, okay, 1 sent data to 2, 2 sent those coins to 3, 3 sent to 4, and so on. So there will be pseudo-anonymity in the system in the case that no one knows who 1 is actually in person, but it's not completely anonymous. Another thing is that the data, it's highly resilient. That is, it's extremely difficult to change the data, as we saw earlier. Because if everyone can read, write, and commit, everyone has the data. So that means that changing of data is not simply, it's just not a matter of making a few changes. You have to make changes to everyone's local copy. So that's not trivial. And the scalability is low. I'll explain why I say that in a bit. Now, if we say about permissioned and public blockchain, you can think something like Ethereum, like anyone can join and read, but only authorized participants can write or commit into the network. That is, not everyone can write data to that network. And since there are not as many participants that are able to write into the network, the scalability increases. That is, we have medium scalability. When we go to private and permissionless, by private, we mean that few participants are authorized to join the network. That is not, it's not open to everyone. Think of a conglomerate of companies coming together and making a blockchain. Let's say Amazon, Microsoft, Google, all of them come together for some reason and decide that we want to have our own blockchain. Then, and only our employees are authorized to join it. In that case, it will be a private blockchain. What makes it permissionless is that if every employee of these three companies can write data into it, in that case, it will make it private permissionless blockchain. And you can guess what private and permission blockchain means. It's basically only authorized participants can join and read, whereas only a subset of those participants can write and commit. The scalability is extremely high for such blockchains. Let's understand what I mean by scalability. So when you are looking for scalability challenges in blockchain, you have to keep in mind these three factors, that are cost, capacity, networking, and throughput. Cost capacity implies the requirement of storing of large quantity of data on blockchain. You have to store the data from the genesis block, that is the first block, to the most recent transactions. However, every node in the blockchain, you can't expect everyone to have the capacity to store such massive amount of information, right? So that's what I mean by cost and capacity. So let's say you had the permissionless and public. Since everyone has the ability to write or commit, then if you want to write to the blockchain, you must have the entire data of the blockchain. So that's why the cost and capacity factor in. The mobile devices don't have such large capacities. The next is networking. In case of every transaction in blockchain, it is broadcasted across all networks, all nodes. Subsequently, a block is again transmitted to all nodes when it is mined. We'll understand mining in a bit. Therefore, the process can consume substantial network resources. That will increase propagation delays, and therefore, it's important to have an efficient mechanism for data transmission. So that's another factor for blockchain scalability. And finally, throughput. Do you know how many transactions does Visa process every second? Any guesses, guys? Okay, I'll tell you. So Visa processes around 1700 transactions every second. And how many does Bitcoin processes? It's 7 transactions per second. So that's what I mean by throughput. It's the time taken to confirm a single transaction. So as size of blocks increase, as we have more transactions, the network will become slower and slower if we don't have the correct consensus mechanisms. So do we have any further questions right now? And I'll come to the question of how Bitcoin uses blockchain. I'll go over it in consensus mechanisms. And you guys can unmute and speak freely. There's no need to write in chat. Okay. Let's understand working of blockchain. Now, let's say that you want to send money to your friend through the network. You publish the transaction and send it to a transaction pool. You can think of a transaction pool as a big bucket where all the transactions are piled in, and miners pick those transactions, whether randomly or through some greedy method. They pick up the transaction, they verify the validity of the transaction, and they mine it. By mining, that is, they calculate the hash and they attach a certain proof that they did the work, and they broadcast it to the network. While verifying, they check all the standard things, such as whether, first thing, the sender and the receiver are valid or not, that is, they exist or not. Secondly, does sender have the money that he or she is paying to their friend? This is a very simplified version of the entire process, but you can think of this as bare bones of how any cryptocurrency works. This is for a single transaction. The miner repeats the processes for, let's say, around 100, 200 transactions and mines the block and publishes it to the network. Once the other nodes validate the the correctness of the block, it's added to everyone's block. So when a miner publishes the block, he or she automatically adds this to his own local copy of blockchain. And now when he publishes it to the network, everyone on the network checks the validity. And if it's correct, they add it to their own blockchain. And through this method, the entire network gets updated of the latest transaction. So first thing, I have a few questions. What do the validators get for the work they are doing? So they are obviously spending a lot of computational resources, right? So what do they get out of it? Any answers, guys? Well, they get rewards. That is, example, Bitcoin miners. When they publish a block, they get 0.25 Bitcoin for every block that they publish. Similarly, Ethereum validators get rewards for the work that they are doing. Also in transactions, you can add a certain fee to incentivize miners to pick up your transaction. It's sort of like a bidding system where you say, okay, I'm willing to pay like, let's say 0.01 Bitcoin for my transaction to go in first and get validated quickly. So the more transaction fee that you're willing to give, the faster the transaction will get approved, because miners will try to pick it up and validate it quickly because they want the reward. And secondly, how do various nodes agree on the validity of the blocks? That is, how do I know that the block that a miner just mined is actually correct and the miner did not do anything fishy, or whether he checked every transaction in a proper way? So that's where we use consensus mechanisms. Let's understand consensus mechanisms. This is a very important topic, and it's a must for any blockchain developer. So I implore you guys to pay attention over here. So consensus mechanism is basically the process of agreeing to a single version of truth by all the people, all the participants in the blockchain network. Let's look at a few popular consensus mechanisms. This is by far the most, by far the most popular consensus mechanism. because Bitcoin uses it. This is the proof of work. Proof of work essentially relies on the proof that enough computational resources have been poured in before any value has been proposed to the network. So a miner has put in tremendous amount of computational effort to make sure that the transactions are valid. This is the only algorithm that has been successful against Sybil attack, where a single entity is operating multiple identities in the network. So in the previous example where I was sending money to Jay, you can think of we have 5 participants, but 3 of those participants are owned by me, and only one other is actually the correct node. So this is proof of work is the kind of algorithm that has proved its resilience against this kind of attack. But as you can imagine, since a lot of computational effort goes in, it's much slower compared to proof of stake, which we'll understand in a moment. So how does it actually work? So think of it this as our block. So our block has Merkle root. I'll explain Merkle roots in some time. I feel I'm repeating myself, but it's just the way it works. You have to understand as you go. And we have the hash of the previous block. Hash of the previous block. We also have transactions in our block. Transactions. And we have the timestamp when this block was actually created. And I'll explain the nonce in a moment. So we have a hashing algorithm. Let's say we have SHA-256. It's just one of those one of the many popular hashing algorithms. It outputs a 256-bit hash. That means we have 64 hexadecimal characters. So we can have A, B, C, D, and so on. We have 64 of such characters. So what happens is we have a network difficulty. That is, let's say we say that for a hash, target hash to be valid, it has to contain a certain number of leading zeros in the hash. So let's say my hash, let's say we have only 5 length of 5 hash. So that is, we have A, 1, 2, 5, and C. This is our hash. But what we want is that the first 2 elements of our hash should be 0. Like they have to be zeros. Then only the hash is considered valid. So this is one of those valid hashes. This is also a valid hash. And how do we change the hash of the entire block? That is, since the hash of the previous block is fixed, the timestamp is fixed, the transactions that we have are fixed. The only thing that we can change is the nonce. The nonce stands for number used only once. So as we change the nonce, the string of the block, that is the hash of the block, changes. And we keep on changing the nonce till we get to the target hash. So you can imagine, as we increase the number of zeros that we want in the start, the difficulty of the problem increases. Currently, we have 5 positions. Every position can have, let's say, 16 possible characters. So I have 16 to the power 5 possibilities. Out of that, if we say that the first 2 characters have to be 0, then the possibility reduces to 16 power 3. So the probability of finding the correct hash is 16 square, right? That is 16 cubed divided by 16 to the power 5. If we want 3 zeros in that case. So you can see that this is a small number. Okay, this is a small number because the length of the hash is really small. Think of it now like the way that we have 64 characters in our entire hash. Over there, the difficulty of the problem increases a lot. Do we have any questions in proof of work? Oh, yeah. And coming to the question, how Bitcoin uses blockchain. So this is the way that it uses blockchain. So it has those blocks and it has the transactions in the block. The miners change the nonce and they propose a value. The proof of work relies on the fact that the solution should be difficult to produce, but easy to verify. Kind of like what professors do. They give us a problem that is difficult to solve, but when they check, they see whether the final answer is correct or not, assuming that it's a fill in the blank sort of problem. And they see whether it's correct or not. And if it's correct, it's easily verifiable by putting the value back or something like that, or they have the answer key. In that case, it's easy to validate. And once they validate it, they give marks. In this case, the miner gets reward. The next consensus algorithm, that is the proof of stake. This is the second most popular consensus algorithm, and it's used by Ethereum currently, Ethereum 2.0 to be precise. So the idea is miners get rewards. In proof of stake, we have validators. It's basically just the change of name for the miners, a different name for the miners, that is. So when validators validate blocks, they get rewards. So the idea is, if a validator, the reward that a validator gets, let's say a validator gets 1 Ethereum, it's an extremely high reward, but we are just taking an example. Let's say a validator gets 1 Ethereum for the block he or she is mining, and his stake in the system, that is the amount that he has invested in the system, is, let's say, 100 Ethereum. In that case, we can be sure that defrauding the entire system won't be in his or her own benefit, as if he or she defrauds the system, in the long term, the value of their own stake will be adversely affected. So if you are getting 1 Ethereum, for 1 Ethereum, you are defrauding the entire system. When your own stake heavily outweighs that does not make economic sense, right? So that's the entire premise of proof of stake. It's designed to increase the network security and reduce the resource wasting, the computational resources that we were wasting in proof of work. Think about all those randomly us trying to get the correct digest value so that we can basically get the leading zeros that we want, right? So this proof of stake has none of it. So the throughput is relatively faster compared to proof of work, and the network security is also good in this case. And the validators are chosen based on the stake they hold. So if you hold 10% of the Ethereum Ether, the coins in Ethereum network are called ethers. So if you hold 10 ethers, 10% of the ethers in the network, your chance of getting selected is 10%. So that's how the validators are selected. They are selected based on the size of the stake that they hold in the network. So do you guys think it's fair compared to proof of work, where, because this entire scheme favors the rich, right? As if you have more stake in the system, you'll be selected more often. So it essentially makes the richer more rich. So what do you guys think? Is it fair compared to proof of work, or less fair, more fair? What do you guys think? Can't hear you guys. Okay. Okay. Okay, I think that's average, as people who don't have big money can't participate. Okay. So won't that be a problem, Parth? Since if because average people make, the bulk of the users. So if only rich have to use it, then it won't be much use to people, right? So average, like people who don't have a lot of money. But yeah, I think I get where you're coming from. Our main is to reduce energy consumption. Yeah, surely our main goal is to reduce energy consumption, but actually it's not the main goal, it's a side benefit that we have. Our main goal is to reduce the amount of time that we take. It might surprise you, proof of stake is actually more fair compared to proof of work. I'll explain why. In proof of stake, if you have 10% stake, you get selected 10% of the time. And if you go to 20% stake, you get selected 20% of time. So you can see that there's a linear correlation, right, between getting selected and the stake that you have. In proof of work, if you want to propose a block, you have to have computing power. Now, the thing is, the money you invest and the computing power you get are not linear relation. When you buy a lot in bulk, so Gujaratis might know this, but when you buy a lot, any business, if you buy a lot of things, you get things in cheap. That it's called economies of scale. So if I have to produce one car, it will cost me a lot. But that if I set up a factory and churn out cars in thousands or 10,000 cars per day, then it will be much cheaper for me. Talking in per car basis. So that's why proof of stake is considered more fair as compared to proof of work. So over here, this diagram explains. So validators have to stake their coins. That is, they have to give the system the assurance by staking their coins and showing that, okay, we won't defraud the system. So let's say Rachel stakes 5 ether, Joey stakes 10 ether, Ross stakes 10 ether. So we have 25 coins, and let's say by random function or through a random function, we select Joey to add a block to the blockchain. He proposes the block and we see that it's valid. So Joey will get the reward of validating all those transactions, but he will not get that money immediately, because the system should have the power to punish the people, in case Joey, defrauded the entire system. So in that case, let's say after 10 blocks or so, Joey will get his stake and his commission for validating the block. Now we can understand delegated proof of stake. This is essentially the same as the proof of stake. It's an innovation on top of it. So the idea is proof of stake favored the rich. But what we do in delegated proof of stake is you get voting rights instead of right to propose the block. So each node that has a stake in the system can sort of put a vote about the validator. So let's say it's sort of a democracy where people take the stand as validators and other stakeholders can vote for a particular person so that he or she can validate the nodes. So that's what delegated proof of stake is. And it's used in BitShares blockchain and other blockchain networks, upcoming blockchain networks are also using this consensus mechanism. It's gaining a lot of traction actually. So these are the nodes or people who are interested to delegate, that is, they want to vote that. And these are the network participants that we have, the stakeholders. These guys can vote, and these guys are there for validating the block. And the network participants vote for their tested delegate, and the selected delegate gets the chance to propose the block. So that's how the delegated proof of stake works. Now, let's come to our last consensus mechanism, that is the practical Byzantine fault tolerance. This is a really, really famous consensus mechanism. So basically what happens over here is nodes that are collecting transactions, that is the nodes that have selected to be the validators or miners, we randomly select, or we can select based on stake that they have in the system, a leader. And the leader orders transactions. Ordering can be done, let's say, from the transaction number or the timestamp or something like that. They order the transaction and broadcast the ordered list to the network. They validate it and broadcast it. Each node that is the what do you call delegate or the validator in the system, they validate the node and broadcast the calculated hash. Then 2/3 of the nodes have the same hash. The new block is mined. So you can see that we have no computational work over here. And since everyone is just broadcasting the same, broadcasting and ordering the list, the throughput should be very fast. So over here, the transactions are really, really fast. That is, they get accepted or rejected really quickly. And so the throughput of the entire system goes through the roof. This is used by Hyperledger Fabric. Hyperledger is an open source initiative that's funded by the Linux organization. That is the guys behind the Linux operating system. And it's funded by them. And it's basically a lot of blockchain initiatives clubbed into under one banner, that is Hyperledger. You guys should really check out Hyperledger. It's really, really good. And if you are serious about getting into blockchain as a developer, then it's imperative that you know about Hyperledger. Any questions till now? Okay, great. Let's understand block structures. Okay. So block structure, this is mainly a Bitcoin block structure, but the essential idea remains the same. We have the block header, we have the transactions themselves, and the transaction counter. So transactions stand for all the transactions that we have in the block, and the transaction counter is the number of coin-based transactions that we have. The field containing like how many transactions do we have in this block, from what number to what number. And it also has the coin-based transaction. The coin-based transaction is a transaction that the miner has. So basically, when a miner mines the block, he gets 0.25 Bitcoin, right? So 0.25 Bitcoins, it's out of thin air. That is, no one is paying him, but he or she can add this transaction as the first transaction in the block, and he can order the rest of the transactions. So this is how, the coin-based, this is considered to be the coin-based transaction. And the block header. Okay, so the block header is the most interesting part of all. So this is the timestamp of the block, the version that the block is using, the Merkle root. We'll go to that next. The difficulty target. The difficulty target was the number of zeros, leading zeros that we want in our system. So as the protocol evolves, the difficulty target increases. The nonce that we discussed earlier, the nonce through which we get this, through which we achieve the hash that we want, and the previous hash. Previous hash is basically the previous hash of the block. So this is the block structure. Yeah, any questions over here? It's pretty simple. Merkle tree. Okay, I really like this topic. Merkle trees are great. Okay, so what a Merkle tree is essentially is, think of L1, L2, L3, L4 as transactions. Okay, we take the hash of those transactions. Transaction, it has all the information that you might accept: the sender, receiver, amount, any specific conditions or stipulations like this amount will only be available to them after X amount of time or so on. So they have all of that information over here. We take the hash of that information and we have this data. That is hash of 0, hash of 1, 1 0 1 1. I feel this is in binary. Okay. Now what we do is we concatenate. Let's say the hash is 2 characters, C and D. The hash over here was 1 3, so on. So now we concatenate these two hashes. That our hash becomes CD 1 3, and we take the hash of the entire thing and we generate a new hash. Let's say it becomes 1 4 6 5, so on. And similarly this becomes similarly the hash of this. So this is sort of like a binary tree, 2 3 AB. And then we concatenate these two and take the hash. So this top hash essentially becomes the fingerprint of the entire data. Now let's say if you change a transaction over here, okay, that will change, that won't have any effect over this part of the tree. Neither it will have effect over here. Okay, so it will change this part. That is, it will change this hash since it's the hash of the 0th element. And since the hash over here changes, since a hash over here changes, the hash 0 will change and subsequently the top hash will change. So you can see that even small changes can be detected, and you can find out which transaction changed over here. And you can even use it in a different way. Let's say you want to verify a specific transaction L2. So you don't have to download data for L3, L4, L1 and get to the top hash. What you can do is you can simply download hash 1 and you can download hash 0. So now you generate the hash of this. Now you have this hash. Through hash 1, you can generate hash 0 and you can combine and see whether the top hash is matching or not. That way you can verify the entire transaction without downloading the data for all the other transactions. So the amount of transactions that you have to download becomes the order of O of log n. I'm assuming that you guys are familiar with big O notation. So over here we can see the space remains the same, that is O of n, since it's a binary tree, balanced binary tree, I would say. Searching becomes O of log n, as you saw over here, top hash, and then we go to hash 0, hash 1, and so on. So searching becomes O of log n. Traversal, if you're traversing the entire tree, O of n. And others are not that useful for our use case, but we have insertion, deletion, and synchronization. Yeah, not very useful for us. You guys might be interested to know that it's used by Git. So I'm assuming that almost everyone who has performed software development in any serious capacity has used Git. So you might have noticed that whenever we changed a file and we run git status, we see that it pinpoints the exact file that has changed. How does it do that? It uses Merkle tree for it. So it sees that, okay, the top hash of the entire folder has changed. So, and then it drills down to see which file has changed. So instead of manually checking each and every file, which would take O of n time, it uses this. So it drastically reduces and uses O of log n. So that's how Git works. And yeah, it's used by blockchain also. How does blockchain use it? Well, you saw over here by the Merkle root. So the normal users that are present in the blockchain, they don't want to store all the transactions. They're only concerned about their own transactions, right? So currently, when I last heard, the Bitcoin network had 144 GBs of data. I think it was in 2021. It must have significantly risen from that time. But you can imagine that normal users don't have such kind of, data capacity, and it's basically wasting of space for them. So what they do is they only store the Merkle root of the block, and they don't store anything else. That is, they don't store the transactions. Transactions are only stored by the miners who are into mining or validating them. So that's how we save a lot of data. So do we have any questions till now? So blockchain, as we discussed, is pretty secure on its own. That is, changing of data is not very easy, but attacks do occur on blockchain. And we'll study 3 of these attacks. And essentially, the attacks that there are on the blockchain, they are called double spending attacks. So in that case, that it's like one of the attacks that's there. It's called double spending attack. It's basically you sending the same coin or the amount you have to multiple people. So in case of physical currency, you can't do that because it's in your hand. How are you going to give it to the same people, right? So, but in case of digital currency, cases might happen where you give the same amount to 2 different people. So that's called double spending attack. And there are more than 3 ways to perform this attack, but we are going to study 3 of them. So let's see Finney attack. So in case of Finney attack, the attacker is a miner. And let's say he has, okay, this is our malicious miner, and he only has 1 Bitcoin with him. Okay. And he has promised Alice that he will give her this Bitcoin in exchange for some service, let's say. So he mines a newly mines a block, and in that block, he adds 1 transaction to Alice of 1 Bitcoin. Keep in mind that he has not released this transaction to the transaction pool. He covertly introduced this into his block, and he has mined the block. That is, he has found the nonce and everything else. Now, what he does is through the network, he sends 1 Bitcoin to Bob and releases the block. That is, since he had 1 Bitcoin, the system was still showing 1 Bitcoin since he did not send it to the transaction pool, right? And the block was not yet mined, not yet released. So everyone on the network still thinks that he has that 1 Bitcoin. So what he does is he sends 1 Bitcoin to Bob through the transaction pool and releases this block. Now, let's say Bob is a trusting guy and he says that, okay, this malicious miner will definitely send me the money. So let's send him the service or the goods before, there's no need of validating the entire thing. The money will arrive when it will arrive out of, goodwill or something like that. So in that case, Alice will get the money because in her block got mined, right? Her block got released and it's there. But for Bob gave him the goods or services and is awaiting payment. But that payment will not occur because in the future, when other miners are going through this particular transaction, that is him sending money to Bob, they'll see that this miner has no Bitcoins left to pay Bob. So they'll decline the transaction. And now what has happened is Bob has already given him some service and he's basically defrauded over here. Does that make sense? So this is what we call as Finney attack. in this, the miner, the attacker has to be the miner. Otherwise, it won't work. Okay. The race attack. This is, I feel, it's a more common sort of attack that can happen, and it can be done by anyone. So what happens is the attacker sends the same coin to different vendors in rapid succession. So let's say we have a miner and who has 1 Bitcoin, and he sends the same Bitcoin through different machines, maybe to 2 different people. And if the vendors don't wait for block confirmation before delivering the goods, they will soon realize that the transaction was rejected later on, since the attacker did not have the coins. Therefore, it's been advised that the vendor must wait for at least 6 block confirmations before releasing the goods. In that case, the chance of cancellation becomes less than 0.1%. So here how the attack works. Okay. So let's say we have our malicious node. He sends the same transaction to 2 different people in rapid succession. Now we have a transaction code, okay, and we have 2 transactions, 1 and 2, and miners are randomly picking up these transactions. Let's say we have 2 miners, miner 1 and miner 2. Miner 1 picks up this transaction, whereas miner 2 picks up this transaction, and they are able to mine the block and release it at the same time. So in that case, we'll have 2 blocks over here, as you can see. This one is containing transaction 1, and the other block is containing transaction 2. Now, since the participants in the network are confused because they don't know which version of the chain to trust, okay, because now we have 2 versions of the chain. So in blockchain, or not in blockchain, I would say in Bitcoin mode, right? In Bitcoin, the rule is that the chain which is the longest is the correct chain. So over here, since the size of both the chains is same, let's say they were both able to mine 1 block. So the size of the 2 versions is the same. So the race goes on. Now let's say other miners join in, and basically the community is now split in half. And there's a race going on of who gets, the blocks, basically. Over here, we have another block. This contains transaction. This will not contain transaction 1. By 1, I mean it has the history of transaction. Its version contained transaction 1, and so on. This race went on till 3 blocks. That is, 3 blocks were presented simultaneously, one after the other. And since the length was same till here, people were confused as to which blockchain can they trust. Now let's say the group 1 was able to publish the 4th block before the second group was able to publish. The network will pivot to this blockchain because it's the longest. It's the longer one of the 2. So now we have this chain as the true blockchain. This is our true blockchain, and this blockchain gets discarded. So all the work that went behind this chain, it's essentially wasted, and the people won't get any money from here. So that's how race attacks work. Do we have any question on how race attacks work, or any question till now? Okay, let's go on to the next slide. This is our last attack that we'll study. This is the 51% attack. Now, do you remember when I told you about the case where I'm sending money to J and we have only one other person in the chain, in the entire network, that's Khushbu. So that's essentially the case where 51% attack can happen. This is a purely impractical attack that is there just for academic purposes. For any actual blockchain, this attack should not be possible. This attack assumes that the attacker owns 51% of the computing power of the network. So imagine that you have 51% of the computing power of Bitcoin network. That is of all the miners that are present and all the nodes that are validating transactions on the network of Bitcoin or Ethereum. You control 51% of the computing power. In that case, what you can do is, like race attack, you can be sure that you can be working on your own fraudulent chain, right? Where you can spend any amount of money you have and you can say that, okay, I'll be spending money that I don't have and so on. You can do any kind of funny stuff over in that your own blockchain. So over here, you have your own blockchain and we have our existing blockchain. So you can be sure, since you contain 51% of the computing power, you can be sure that at some point of the time, your chain will become longer than the true blockchain. And since we accept the longer blockchain as the true blockchain, your blockchain will then become the correct blockchain. And in that way, all the fraudulent transactions that you did earlier will become the correct transactions. And so, you can defraud everyone on the network like that. But owning such huge amount of computing power is like impractical. So for Bitcoin, if you want to perform this kind of attack, I feel that you need to have $44 billion or something like that. And then this kind of attack will take time. $44 billion, and you need to invest it into computing power alone. So if you have that kind of money and you are willing to spend it, then you can perform 51% attack on Bitcoin network. And it's a fictitious attack, as I mentioned, and since it's prohibitively expensive to perform such an attack. Yeah, do we have any questions? Now, let's come to smart contracts. These are really, really interesting things that like I feel that they should be the basis of our future as we go forward. They'll become the norm, I feel. So smart contracts are basically programs that are stored on blockchain network and they run when certain conditions are met. So they are basically an if and then kind of scenario. If all of these conditions are satisfied, then execute this command. Execute this command means it can be transferring of money, it can be transferring of something else. I think we have a hand raised up. Maybe if someone has raised their hand, they can ask any questions that they might have. Okay. I feel I might have been mistaken. Okay. Anyways, so smart contracts, yeah. So since the entire process is automated, there's no intermediary involved and the time loss will be minimal since it's automatically executed. So the major benefits of smart contracts are speed, efficiency, accuracy, trust, transparency, security, and savings. I feel almost all of them are self-explanatory. Trust, you can have trust in the system because no third party is involved. It's basically you have written the contract or someone else has written the contract. You don't have to trust them, the other party, to uphold their end because everything is done through a blockchain. So trust gets automatically built in to the entire thing. And transparency, again, because it's stored on a blockchain, so it's transparent for everyone to see. Security, obviously it's blockchain, so security is there. And savings, because you are not involving any third party. So there are a lot of savings if you follow the smart contracts instead of going with the traditional legal contract. Okay, so these are the 4 properties of the smart contracts. First, and the mandatory properties are that it has to be automatically executable. So as soon as the conditions are met, the transactions should go through, and no one has to present a form somewhere or something, anything like that. It should be instant. The second thing is it should be enforceable. That is, as soon as the conditions are met and everything is in place, you should be able to enforce the contract and on its participants, so that neither of them can back down from it. Now, the next two things, they can be relaxed, but they are good to have in our smart contract. That is, it's semantically sound, meaning that it should be understood by layman. Like, it should be simple so that even a lay person can understand it. I'll show you an example of a smart contract shortly. And fourth, it should be secure and unstoppable. So this is a bit debatable, but basically there are ways that you can stop a smart contract from happening, or it's not entirely secure, but we won't go much deep into it. It's basically all smart contracts need to have this property. Decentralized application, just a big word, nothing to be afraid of. Decentralized application is basically smart contract with a front end. So like on Ethereum blockchain, smart contracts are accessible and transparent. They are like open APIs, anyone can call them, and so on. So let's say you have a smart contract. So you can build a smart front end to interact with that smart contract. Let's say you have an asset management system. We'll see an example of that shortly. You can call that smart contract since it has open APIs, and you can interact with it. And the decentralized application has its backend running on peer-to-peer network or some Ethereum virtual machine. Yeah, blockchains can't be hacked. By hacked, I feel that you're specifying the attacks. So as we saw, the attacks can happen on blockchain, and attacks have been like they are there in blockchain, but usually it's not as easy to perform attacks on blockchain. So smart contracts are basically programs. So no, they can't be hacked. They're immutable. So people are working on making smart contracts upgradable, but they can't be. Yeah, surely I'll share the slides. But they can't be mutable. It's not as trivial as upgrading any program. Since it's stored on a blockchain, it's not easy to mutate the entire thing. So you can contrast this with some backend code running on centralized server. So if a particular server is compromised, the entire app gets compromised, right? But over here, since it's decentralized, even if a single server is compromised, the rest of the network is unaffected because multiple copies exist. So I'll be demonstrating a decentralized application, and in there I'll show you a smart contract. First, I'll show you this was made by me and my team during our blockchain course in the college. And special thanks to my teammates, Hardik Parnami, Shrishti Sharma. They are great guys. You can check them out. I have attached their LinkedIn profiles over here. But let's see asset management system. Okay, I'll first show you the demonstration, then we can go over the entire thing. Oh, also, Khushbu, can you let me know if you can hear the things what's being said over here.
Yeah, sure.
So is the audio, are you able to hear?
No, I think it's not audible.
Maybe I'll have to reshare. Yeah, it's not audible.
No, still not audible.
Okay, yeah, sure. I'll do reshare. What about now?
No, not yet audible. I think you can change it from the sharing options. Share with computer audio.
Sorry.
A decentralized application. Today, we'll demo.
It's okay now?
Yeah, it's now audible.
Okay. I'll stop in between and try to explain what's going on. But in the meantime, let's see.
Demonstrate the working of our decentralized application. We have built an asset management system. My team consists of Shrishti Sharma, Hardik Parnami, and myself, Tanay Gupta. Managing assets such as property, plant, equipment, land, and paintings has always been a difficult task. Proving their ownership has been even more so. Our project solves these problems using blockchain technology. Since blockchains are difficult to tamper with and can provide a clear chain of custody of various assets, they are a natural choice for solving the above problem.
So basically, we have built an asset management system over here. So you guys might have experienced this yourself in your day-to-day life with your parents, or just reading about it in newspapers, that it's extremely difficult to prove ownership of land, and especially in cases of inheritance, or when you make a land deed or something like that. Sometimes the loan is there on land and the builder has not informed you of the same. In all of these cases, because you were not aware of the asset and its ownership, the chain of custody that the ownership has, like the chain of custody that the land or any asset has, you were not able to make an informed choice and you were defrauded. So you can think yourself that in this case, if you have blockchain, you can view the entire chain of custody over the time for a particular asset, and you get to reduce the intermediaries that are present. In that case, whenever you want to reduce the intermediaries and see the chain of custody, blockchains are an amazing choice. So let's move forward.
We have used Ganache to simulate local Ethereum blockchain and MetaMask to store and manage account keys, broadcast transactions, send and receive Ethereum-based cryptocurrencies and tokens.
Okay, so when you are developing smart contracts, so you would like to test your contracts, right? You can't be sure that you wrote a correct contract in the first go, and secondly, you can't be sure, you can't test it, your contract on actual Ethereum blockchain. So Ganache is a tool where you can simulate an Ethereum blockchain, and you can it will act as a proper Ethereum network itself, and you'll be able to simulate all the transactions over here. So Ganache is a great tool, and it should be definitely in your tool belt, that you can use it and develop cool smart contracts.
We have deployed Ethereum-based blockchain on our local network, and now we'll import these accounts to MetaMask.
So MetaMask is basically an extension, or you can say it sort of manages your wallets. So wallets hold the currency that you have. Ethereum, Bitcoins, you can have multiple currencies. So MetaMask connects to the blockchain network, maybe Ethereum. In our case, it's a local blockchain network. It connects to it and it shows us all the various currencies that you have, ethers, bitcoins, and so on. So MetaMask is essential. Over here, you can see this is your private key. Now, private keys are extremely, extremely sensitive. Since this is just a local blockchain, it's okay if you even share, like I'm showing the private key. But if you go in the real world and you have real Ethereum account, a Bitcoin account with your own private keys, you should safeguard it with your life. Because if someone has access to your private key, they essentially have access to your entire account, and your funds will definitely disappear if someone else has access to it. So
We can do this by copying the private keys and pasting them into MetaMask. Let's rename this account.
So this is just essentially us adding the
to
accounts
Tanay.
and so I'll forward it. We add 4 such accounts. That's Tanay, Hardik, Shrishti, and John. Okay.
Now, Hardik will demonstrate the working of our system.
Hi, so I'm Hardik, and now we'll compile our smart contract. So it's compiled, and now we'll deploy it. So for deployment,
We'll go over the smart contract in a bit. If you're wondering in what language this is written, smart contracts are mainly written in Solidity. It's a non-Turing, it's not a Turing complete language since it does not have loops. And it has certain restrictions in place so that infinite amount of resources are not wasted in running a program. So the entire contract is written in Solidity. It's a pretty easy language to pick up. You can pick it up in a few hours.
only the admin can deploy the smart contract, and let's set Tanay as so it's compiled, and now we'll deploy it. So for deployment, only the admin can deploy the smart contract, and let's set Tanay as the admin for the smart contract. Right. So we need to confirm the transaction.
Admin here means the administrator, like the person who will own the smart contract. So let's say I'm creating a company sort of thing. So I'm not owning the blockchain. Please keep in mind that I'm just owning this smart contract. I'm just putting it out as a software that anyone can use. People can join, pitch in into the smart contract, and they can become a part of it. So I will be the administrator of the smart contract.
Yeah, so the transaction has been done, and now the smart contract has been deployed on the blockchain. So now we need to do one more thing and copy the address and paste it in our implementation. Now all we need to do is
this is the front end that will connect to the blockchain network.
Start the app. So this will be our front end for the asset management app. The front end for our asset management application. So now first we'll need to add wallets for all 4 of the users. First we'll go to the user that is, okay, so we need to connect all the users to our front end. So we connect.
Okay, so before we go forward, let me just explain you what the entire thing is. So we have 3 kind of people in our implementation. Those are the administrator, that is me, the one who manages the entire application, the entire smart contract. The administrator has certain rights that no one else has, that is supporting different types of assets. So as a company, you can always think in, from the customer point of view. So as a company, your customer wants you to support various assets such as land, paintings, NFTs, but you may not have the correct infrastructure to support it yet. So what you want is you want a smart contract that can be upgraded over time to support these things. So the administrator will have the power to update the contract so that it can support various assets. And this is one of the special powers that the administrator enjoys. The administrator also enjoys another power, that is adding validators. So what the business idea was, that there will be an administrator who will manage the entire thing. And then there are validators. By validators, it means that, let's say that Khushbu owns Mona Lisa and she wants to put it in our network so that other people can buy it from her, or just for showing us that she owns it. So there have to be some validators that can actually, come and see that she actually owns the painting or something like that, and trust and see that it's authentic. So that's the role of validators, and only validators can add specific assets into the blockchain. That is, only they can see that, like, let's say Khushbu owns Mona Lisa and Hardik was the validator. So Hardik will check if the Mona Lisa is authentic, and then he will add it to the network. And Khushbu can also add the amount she's willing to sell it for, and so on. And then there are owners. So in our case, Khushbu will be the owner of the asset, that is Mona Lisa, and she will have the right to sell it at any point of time in our network. And you can think, it has certain caveats, that what if she sold it somewhere else first, but we are, keeping it simple for now and saying that such things are not possible currently, because this was just a demonstration. So basically, the entire thing has three people: administrator, validators, and owners. So do you guys have any questions, or can I move forward? Okay, I'll take that as a yes. Okay. So the data that will be stored will be the list of supported assets that we have, let's say painting, NFTs, land, the mapping of validators and the type of assets that they can validate, and the wallets and the assets that they need. Let's see.
Tanay. We need to connect Hardik to connect Srishti and our dear friend John. So now we need to add wallets for each of these users. So we'll just go here and copy the address for John and add wallet. So in our implementation, anyone can add their wallets. That's why John is adding his own wallet. So
when a guy or gal adds a wallet, they are essentially becoming part of the smart contract. So that's what we mean by adding wallet. So adding of wallet should be, so anyone should be able to become part of it. So it's a public system. See, you can pick up on these keys, that this is a public system since anyone can join it.
John will need to approve the transaction now. He approves and the transaction has been done. Now we'll do the same for the remaining 3 users.
Now everyone else will also become part of the network. So that happens.
To add the types of asset which are allowed in our smart contract implementation. So for the demo purpose, we'll only add a painting as asset type. So we'll do painting and we'll click the button. Now since I'm Hardik and I'm not the admin, so this transaction should fail, which has been shown in the demo and in our smart contract as well. So even if we confirm over here, so the localhost will show that there's an error and we need to switch to admin and then do this transaction. So admin is Tanay, as we saw before. And now if Tanay does this transaction, so now there will be no error and he should confirm this. So the transaction has been done.
So you can see that MetaMask warns us that a transaction will fail because anyone can read the the script that we have there on the blockchain. So anyone and everyone can view it, and since the wallets have access to it, they can pre-run it and see that, not pre-run it, they can check conditions and see that okay, it's going to fail and warn us.
And then we need to add validators as well. So what we thought was I'll be the validator for painting, and let's switch to my address. I'll copy this address, but since Tanay is again the admin, so Tanay should do the transaction, and I'll add the address and the asset type. So address is my address, and then the asset type is painting. So now we'll add myself as a validator for painting and confirming this transaction, and I'm therefore added as a validator. Now Srishti will take over.
Hi, I'm Srishti. I will demonstrate adding, buying, and selling of assets on our system. Let's say that John wants to add the painting Mona Lisa as his asset. Since Hardik is a validator of paintings, only he can validate and add this asset under John. So that's the name of the asset. That's the type of the asset. And the address for John. But then we'll have to switch to Hardik's account because he is the validator and only he can add the asset.
So you might be confused as to why we have multiple accounts. So you have to understand that in the real world, if this app was deployed, each and everyone would only have access to their own account. So in my computer, I would have my own account. Hardik would have his own account in his computer. Same for Srishti. So over here, we are constantly switching between the accounts because this is just a demo and we have access to the demo accounts that we created for everyone.
And here we will confirm the transaction. The transaction is confirmed. Now let's say that I want to buy the painting Mona Lisa from John. For that, John needs to give his consent to sell it. And suppose John sets the price to be 5 So we'll have to give the name of the asset and the price for the asset. The transaction is confirmed. And now I can buy the asset Mona Lisa from John. How we can buy and sell assets in our system. This concludes our presentation.
So you saw how an example of a decentralized application. So now we'll see. Oh, okay. So I'll tell you about this. Remix is the IDE which supports Solidity, which is the language that we'll be using to write smart contracts. And basically, we used JavaScript for our front end. So, okay. So this is basically our smart contract. That we have an asset. So every asset has an address that the address is the type. So it's basically an integer sort of thing, integer boolean sort of thing. So address is another data type that will hold the address, the Bitcoin address of the owner. Consent to sell, which is true or false, and exists. Exist is because let's say the asset no longer exists on the blockchain. That is the user, bailed out from our program, then the exist flag will set to false. Since in blockchain, we can't delete assets, right? Delete stuff, right, from blockchain. So that's why we have this billion. And then we have a price to sell, which is basically the price the owner is willing to sell it for. For every wallet, we have certain things that is validator. This condition is to check whether the wallet is validator of a certain asset type and exists, same as the above for the asset, whether the wallet exists in our system or not. So we have the address of admin. This is when we're initializing the contract, it goes into a sequential manner, and we initialize a variable called admin. Then we have a mapping string to boolean that gives us the supported assets. So since we want to store the supported assets that we have, we did not want to have an array because checking that array would take time, and I'm not sure whether Solidity supported it in a strict sense or not. So that's why we have a string. Again, this is a demo. I'm not saying that these are the best practices or anything. Then we have a mapping from address to the string that stores the validator to the asset type that the validator can validate. So Hardik would be mapped to painting over here. And then we have our accounts. Accounts basically store the address to the wallet. So wallet is a structure over here. So we store the address and its corresponding wallet in a network. And this is the address to asset. That is, we have our mapping from a particular address. That is who owns what, basically. This is the mapping that shows that. Okay. Now we have various functions such as add validator, add wallet. So what Solidity supports is certain things like this. You can see that we will require that the person who is, checking, who's trying to add the validator is the admin or not. If he or she is not the admin, then we'll present an this error message that only the admin can add a validator. And similarly, we have certain conditions. So like we mentioned, if and then. So our if conditions would be that someone has to press the button. The other condition would be that the sender should be an admin. The asset should be supported by us. So the asset type, the painting type should be supported by us. The validator address should exist. And the validator should not already be present. Like the validator should not be validating something else and so on. So you see, these are the if and then kind of things that I was talking about when talking about smart contracts. Similarly, we have other things, add asset to blockchain, add supported asset, and so on. And we have APIs for these that can be called through our front end. So this is basically it. Any questions that you have? Okay, this is one of the this is a very famous blockchain use case selection framework. That is, how can you decide whether you want to use blockchain or not? So there are various steps. I know the image is not clear, but this was the best quality image that I could find. But you can write it on the net and see whether you should, to find this framework, and this will tell you whether you should use a blockchain or not. Basically, if you have a solid idea that would benefit from reducing the intermediaries in between, like brokers and something like that, you have digital assets instead of physical assets, then that would be good. If you have physical assets, then you should have some tokenomics. Tokenomics means token economics. So like Bitcoin. The value of Bitcoin was, I think, 33 lakhs or something like that for single Bitcoin. So this is called a tokenomics model. How will the economics of the token change over time, or how do they work? That's what's covered by tokenomics. So you should have a tokenomics model for physical assets. If otherwise, it's best if you have digital assets. And would your does your application require rapid transactions? So we saw that blockchain is not yet efficient in having rapid transactions, supporting rapid transactions, or by the time that someone else is watching this, maybe blockchain has evolved and we have better consensus mechanisms to support that, or we have some other mechanism through which we can have greater throughput. Then we can use our blockchain in that case, and so on. So there are various if-then cases that we should keep in mind while choosing whether we want to select blockchain for our business use case or not. Sure. Okay. Before we go on further, I want to do an activity that's, can you guys think, like after this workshop, can you guys now think of some use case where you can apply blockchain? Present your solution and, explain why you chose blockchain to solve the specific problem. And if you can, explain the business aspect of it, that is how you'll make money out of it, that will earn you additional points. So can we have, what do you call it? Breakout rooms over here, and then we can continue further.
Yeah, sure. Like, how many rooms shall we make?
Let's see how many participants we have. 37. I think 7 people each, and 2 people will be extra. Like 2 groups will have 8 people, right? So if we can have breakout rooms, that will be great. I'll switch between them and we'll discuss.
Okay, so I'll create 7, right?
Yeah. 7 groups. Okay, fine. 7 rooms. In the meantime, someone asked a question about hard fork that happened in Bitcoin, right? You're talking about that, right? Or Ethereum. Actually, I'm not sure of that, but I think something of that sort happened, but I'm not
Yeah, so am I audible?
Yeah.
So participants, this is basically we are dividing you all into different groups so that you can discuss and share those ideas, and then sir will join basically each room or each group, and then you can share your ideas or whatever you have discussed with him accordingly. That's why we have made different groups, because you can think in small groups and share your ideas. The whole bunch of participants will make chaos in this meeting. If you have any doubts, just let me know here, and then we can move on to create those rooms.
Basically, you can think of any use case where, having a distributed, decentralized system would help. So places where you have to reduce intermediaries, or places where, it would be good to have immutable state. That is, no one can change the states that we have, and no one can alter the data. Or if someone is altering the data, you should know about it. Anything like that. So any such use cases that you can think of, it's fine. Even if it's basic, it's fine. The idea is to get you thinking about the business aspects of blockchain.
Shall we proceed and make those breakout rooms? Kindly give me a yes or no in the chat, participants. If everyone is clear with the idea, we can proceed and make those breakout rooms. Okay, so I'll make 5 breakout rooms. So like we can have 5 participants in each one of them.
Wait a second. I feel that participants are not yet clear, not about what to do, but in general about how it can be used or so on. So maybe I can share some cases where blockchain has been used, and then I'll share about how to become a better blockchain developer, how people can begin on their journey of developing.
Yeah, that would be better.
Yeah, that would be great.
Yeah, okay, sure, I'll do that. Let me just share my screen. Okay, so some ideas. Okay, is the screen visible?
Yes, it's visible.
So some ideas are a cryptocurrency bank. So there are already existing ideas like this. So for example, what do you call? Forgot, Wazirex? No. Also, there are apps basically where you can lend money. So what a bank does, it has some services such as loan, FDs, and so on, where you can invest stuff and those sort of things. So one idea is to have a cryptocurrency bank where users can deposit their money, gain interest on it. People can loan out money, others can borrow money, and so on. In here you will see that since there is transparency and immutability, so people can't defraud the system very easily. So that's why, yeah, peer-to-peer lending, exactly. So we can have that as well, peer-to-peer lending, and we can have entire systems and smart contracts to support that. Then we have social networking for artists. So you might have heard recently of Facebook, people have posting allegations that people are stealing their content and posting it on Facebook without giving proper sources and so on. So what you can do is you can post your ideas on the blockchain, and since that idea has specific roots, that people can see the chain of custody, you'll have the ownership of that data. So we can have that social networking for artists. By artists, I mean anyone who does creative work and who wants to keep the ownership of the data, of the content that they create. So that's what I mean by social networking for artists. Similarly, for e-voting systems, so voting systems, like this is like a fun one. Voting systems require anonymity, and we have anonymity in blockchain. That is, people don't know which ID, which wallet ID belongs to which person. So that gives us anonymity, and the things such as, tampering with EVM machines and so on, that cannot happen in smart contracts. So e-voting can also, obviously, it requires us to do a lot more thinking of use cases and so on. So those are some ideas. Now, I understand that it is very difficult, to come up with ideas just after you learn about blockchain, especially the basics of blockchain after exactly a patient healthcare, where, for example, patients, we have another aspect that Parth said was healthcare. So this is a popular one where patients put their data in blockchain. In that case, other doctors can access it very easily. And one other profit is that, patients can gain money out of, providing that data to other services. So for example, you are compiling a database to train a machine learning model, let's say, and patients can voluntarily provide their data on some nominal fees. So that in that case, blockchain can come into the picture and help them out. That's the idea over here. So that is, you will, at the end of the day, you can see that the crux is that the owner should have clear custody of the data or the coins or anything else that they have, the data that they have. So that's the idea over here. So yeah. Also, let's see. So yeah, as I was saying, it's difficult to come up with ideas, especially when you are just starting out with blockchain. So I've added some information of how to become a blockchain developer. So let's say you want to break into it. So this was just an introductory session. We have a lot to learn. Like, I have a lot to learn, I would say. So it's, just have that mindset of learning. Don't think that you are an expert because you attended some seminar or something, or even if you did some work. The most important thing is to get some hands-on work in blockchain. So if you want to become a blockchain developer, it's a really upcoming field, and I feel that there will be a lot many job opportunities. Or why go for a job when you can, start something of your own? So I would say startup opportunities, great startup opportunities, and don't be discouraged by, the decline of the cryptocurrency that's happening over here. I'm not endorsing any cryptocurrency. Please don't take it as an investment advice. I'm just saying that all these ups and downs happen, and blockchain is much more than cryptocurrency. So please focus on that and don't get discouraged by this. So if you think about blockchain development, we basically have two varieties of job that are currently core blockchain developer. That is, you are actively participating in creating the infrastructure that can be used by other participants. So for example, you can think of Hyperledger. That is, you are actively developing consensus mechanisms that we discussed. So as you saw, we have a great need for good consensus mechanism to have a higher throughput with good security. Then the second type of job is the blockchain software development. So while constructing the decentralized application, you saw that we wrote a smart contract on an existing network, and then we deployed it, created a front end, and so on. So that all comes under the purview of blockchain software development. So these are the two major types of roles that we have in blockchain industry. And these just go into more details, that are designing blockchain protocols, designing and monitoring network architecture, and so on. Basically, you will implement features and functionalities. Now for blockchain software developer, front end, back end. So you should be really proficient with JavaScript and so on. So you can see that you don't have to learn something entirely new. You know, everything builds upon itself. So if you have learned cryptography, you know, blockchain builds on top of cryptography. So you can, you know, move forward. Development and implementation of smart contracts. So if you're developing any application, the first thing is that you should know good design principles. So those will come in handy over here. Then developing APIs. So as we saw that Ethereum has open APIs, many smart contracts have open APIs. So developing APIs for blockchain integration. So the first thing that not only blockchain developer, for any developer, is to be proficient in data structures. Then they should be, then for blockchain developer, they should have proficiency in networking, databases, and cryptography. System design, you develop as you go forward, that there are various books that you can follow for system design. And one should have a good system design, you know, one should keep in mind good system design principles while designing a system. The most important thing, you should understand how blockchains work in depth. So I hope that this presentation gave you some idea of that, but there's still a lot to learn about in depth how Ethereum works, how Bitcoin works, how are they different, what additional features does Ethereum support, what that Bitcoin does not, and so on. Then you should learn about cryptonomics, that is, how does the economy of cryptocurrency works. So if you want to break into development of cryptocurrency, and then you should learn about Ethereum and decentralized applications. That is how they work, how do smart contracts work, how are they deployed, how do people interact with them. Now, for developing smart contracts, you should learn Solidity. And finally, the most important thing is to get hands-on experience. So there are many many projects that you can search on internet, and you can learn how to create. There are many videos, then you can learn to create smart contracts. You can create decentralized application, post it on GitHub, and, you know, maybe make a LinkedIn post about it. Show people that you have made something cool. Show them that you know how decentralized applications work, and so on. Okay, this is for further reading. The last two links are for the books that are Mastering Blockchain and by Imran Bashir, and Bitcoin and Cryptocurrency Technologies by Arvind Narayan. So these two books I recommend if you want to learn more about Bitcoin and blockchain, Ethereum in general. And these are few of the topics that I think that you should read to get better understanding. I'll share these slides with BTV community and everyone who's here. Maybe the organizers can forward it to the participants. So over here you can learn more about. Okay. I heard that someone was asking me about the hard fork that happened in Ethereum a few years back, I feel in 2016 or so. Stop sharing. Okay. So basically what happened during that time was there was a DAO. DAO stands for Decentralized organization, I think, decentralized organization. So it's like a mutual fund where you pool in your money and they earn you, they get you more money. Basically, it's an investment sort of thing. So it was a huge DAO, I think some millions of dollars worth of DAO. And what happened is it was struck by attackers. And those attackers stole a lot of its money. That was, I think, all of its money that was present in the DAO. Now, this was, the beginning of Ethereum. Not the beginning, but I would say that it was still new. So the community, the Ethereum community, and the creator of Ethereum sat with his or her colleagues, and they had discussion whether they should roll back the changes. So what can happen is all the money that has been transferred through from this DAO has left a trail. So the idea was, should we roll back all these transactions and create a separate chain? So over here, the hard fork happened. So the community was split on this. Some people were saying that Ethereum should not intervene, that the idea is that it should not be ruled by certain body, or so it's not good that we are, every time something wrong happens, we roll back everything. And some people were of the view that people should not lose money when they are investing on this platform. Not lose money through fraudulent means, like losing money through economics is fine, but losing money like someone stole it is wrong. So the community was split on it. So at that time, a hard fork happened. By hard fork, it meant that the Ethereum network split at that time, and it essentially created two Ethereum blockchains. One is Ethereum as we know it, and other is Ethereum Classic. So Ethereum Classic still has that amount, and the stolen amount, people don't have not recovered that stolen amount in Ethereum Classic, whereas in the Ethereum that is more famous and we know about it, it's the Ethereum where the creators rolled back all the stolen money and essentially gave it back to the people who owned it. And yeah, that's the hard fork. In hard fork, all the people have to select which version they are supporting or which version they are choosing. So in hard fork, even the nodes that are just the participants are not the validators, they have to participate in it and actively make a choice of which version they'll be supporting. Usually hard forks are rare and they don't happen as often as soft forks. Soft forks are like planned upgrades into protocol and those sort of, like, you can think of them like app upgrades, where only validators have to update their protocols, and the normal users can go on using the entire thing and they don't have to update anything. So those are called soft forks. It does not split the network into two, whereas hard fork splits the network into two. So that's what happened in Ethereum. Is that clear? Guys, that's it from my side. If you have any questions, please ask them now, or you can reach out to me on LinkedIn. I'll respond to any messages that I get there. So yeah, please do reach out. Please send me a connection request. Got the idea? Time. Oh, okay, I've got a question. As blockchains are decentralized, don't you think it's a wastage of memory? Yeah, maybe you can think of it that way, but the advantage of that is that no single entity owns the data, right? So if you put your data in Google, it's essentially, if you read terms and condition or something like that, Google owns that data. I wouldn't say own that data, but has control of the data. Or same for any other company, right? So decentralized gives you control of your own data. So yeah, it's obviously wasting a lot of memory, but it gives you the advantage of, owning your own data. And one other thing is you don't have to store your data. You only have to store your own data and not other people's data. For example, in transactions, if you are in Bitcoin, if you are just a normal user, you don't have to store all the transactions in the Bitcoin network, like 144 GB of data. You only need to store the blocks and not the transactions. So the Merkle tree that we discussed, you only need to store its root and not all of the information. So yeah.
Okay, so do you have any other questions? We still have time. You can unmute yourselves if you want to ask something. Okay, so looks like we don't have any further questions. So thank you so much, Tanay sir, for being here. And okay, we have a question.
Race attack, if we consider the longer chain, the data validated by the shittier chain will be lost, or we have to validate it again? No, it's essentially not lost, I would say. It goes back shorter chain. Okay, shorter chain. So yeah, the information is not lost. It just goes back into the transaction pool, according to me. And you have to, validate them again. You need to get them validated again. And maybe the data validated if the transactions are not overlapping. Let's say, like the example I took, the transaction 1 and transaction 2, you only have those transactions. Then, yeah, the effort is definitely wasted, but the data is secure. Like you'll get chance to validate the data again. Like the other miners will pick it up as the longer chain propagates further. But the effort that other miners put into growing the shorter chain was definitely wasted. So that's one of the shortcomings. You see, in proof of work, you can imagine how much computational resources were wasted to grow the shorter chain, and in the end, it just got wasted. Ethereum deals with this through its own way. It uses the most work done, the heaviest chain instead of the longest chain, but that's an entirely different topic. And I think that as you'll study Ethereum in depth, you'll get to know about it. It's really good, and you'll see that Ethereum is, far more developed, I would say, in terms of its features like this. So it's growing rapidly. Yeah, I'll share the PPT. Don't worry, I'll send it to the organizers and they can send it to you guys.
Okay, so if we don't have any other questions, then let's conclude the workshop, shall we?
Yeah, sure.
Okay, thank you so much, Tanay sir, for being here and presenting such an amazing session and showing us the demo of your asset management system. It was a really wonderful learning experience for all of us.
Thank you everyone for attending. You were really great, and thank you BTB for having me. Thank you so much.
Thank you so much, sir. So let's end the workshop. Thank you everyone for being a part of this workshop. We hope everyone enjoyed, and we really look forward to seeing you in the next events as well. And we'll be sharing a feedback form. So please make sure that you fill in the feedback form to let us know how much you liked our workshop and if you want us to improve any further. And it will be followed by some of your details so that we can make your certificates ready in few days. So please fill in the whole form. And please register in the hackathon if you have not done yet. Also join the Discord server because it's really mandatory to get the informations of the further events as well. And stay connected with our social media to stay updated. So that's it. Thank you everyone for joining. Have a very good day.